Welcome back. In this lecture, we will introduce electrochemical kinetics, and we'll also see that double layer, an electrochemical double layer, plays a central role. This is an introductory lecture. We will have a more quantitative description in the next few lectures. In the previous lecture, we had addressed the issue of activity coefficient and an important model for its calculation, which is the Debye-Hückel theory. So we had earlier seen that the electrochemical potential is defined in the following manner. And as you can see that activity is related to electrochemical potential. In other words, you can formulate all issues of phase equilibrium using activity instead of using chemical potential. Both are equivalent formulation. Either we can use chemical potentials or you can use activity. There's one-to-one correlation between activity and the chemical potential. Instead of using abstract definition of activity, we can take certain systems like gases and give the definition of activity. For example, here we are giving the definition of activity of an ideal gas. First thing to notice is activity is a dimensionless quantity. So the activity of an ideal gas is defined as partial pressure of that species whose activity is being considered divided by a standard state. So the partial pressure can be computed in the following manner: mole fraction times the total pressure divided by a standard state, which we take to be this number. In this case, we are considering the gas mixture to be ideal. For the systems that are of relevance to this class on electrochemical engineering, gases are not that important. What is more important are activity of species present in a solvent, electrolytes and non-electrolytes. Here, what we are plotting is activity in the y-axis and concentration in the x-axis. This is a line wherein activity is equal to the concentration. And we are plotting for two different systems. The green curve is the activity for non-electrolytes, and this purple curve is activity for electrolytes. What you should observe is that at low concentration, activity is equal to concentration. However, as concentration increases, the deviation from this linear line is more and more, and it's much more for an electrolyte compared to a non-electrolyte. So for an ionic solute in solvent, the activity is defined in the following manner. Activity coefficient for activity for a particular species I is activity coefficient times Ci divided by C naught. C naught is a standard state given by this number. So why is there a deviation from the straight line? The deviation from the straight line is because of solute-solute interaction. The solute-solute interaction is greater when you have an ionic solute, and it's lesser if you have a non-ionic solute. So in all these cases, when you're considering an ideal solution, what we mean by ideal in that case is the solute interacts only with the solvent. It is not interacting with any other solute ion. Right? So the whole issue of defining activity for ionic solute boils down to developing models or experiments, computations to get the activity coefficient. So there are inherent difficulties in getting an expression or making such measurement. First, even though we define an activity for a particular species, it is not possible to introduce either a cation or an anion in isolation into a solvent. It is only possible to introduce an anion and cation in a controlled manner only by introducing a salt. It's not possible to just introduce Na plus or Cl minus. Okay, so that is one of the issue. So always we are introducing a salt, which is indicated here, and the salt which we are considering it to be a strong electrolyte. Therefore, they will dissociate in the solvent, completely dissociate in the solvent. We also have an intuitive understanding of what is the limiting behavior of activity at low concentration. At low concentration, the distance between a solute and another solute is so large that there is no interaction between them. Therefore, we have a limiting behavior that the activity coefficient will tend towards 1 as the concentration goes towards 0. So we have an asymptotic behavior for gamma I as Ci tends towards 0. So with these being the constraints, we define the mean activity coefficient for a salt. A salt is being introduced. We can re-express the activity formula for activity in this manner. This is just an expression. We have not yet developed any models for activity coefficient. All we are emphasizing here is we can only discuss activity of an ionic species via a discussion of ion activity of a particular salt. So M is the molality. This is the mean ionic activity coefficient. Nu is nu plus plus nu minus, and all these definitions we elaborated in the previous lecture. And then we can build certain models for activity coefficient and then multiply that activity coefficient with by concentration, get the activity related to chemical potential. Once you have chemical potential, properties like phase equilibrium, colligative properties can be computed, and the experimental measurement of activity, which depends upon mean activity coefficient, is obtained by measuring properties of phase equilibrium or colligative properties. Okay, so most of these experiments are done, for example, by measuring colligative properties, depression in boiling point, elevation in melting point, and so on. So here, a mean activity coefficient is plotted against ionic strength. This is an important feature of an ionic solution. We define what is the ionic strength, which depends upon the concentration of solutes present in the system. As you can see, when the ionic strength becomes lesser as it tends towards 0, that means the concentration of the solute becomes negligible. The mean molar ionic coefficient also tends towards 1. And as the concentration increases, the deviation from 1 is greater and greater. So that mean molar activity coefficient is only mentioned here. This is obtained from via experiment. It can also be computed for a particular salt, NaCl and CaCl2. So we cannot mention mean activity coefficient for a particular ion. We also mention how do you define activity coefficient for electrons. So this is activity coefficient for an electron in a metal or an electronic conductor cannot be measured in isolation. It can be measured against a potential difference between two electronic conductors. if you know the potential difference between two ionic electronic conductors, we can obtain the ratio of activity of electron present in one of the electronic conductor divided by the activity of the electron present in the other electronic conductor. And this is the potential difference between the two electronic conductors indicated here by 1 and 2. All right. Then we moved on to giving certain aspects of the Debye-Hückel theory. So why is it being used? The objective here is that we argued that the deviation of activity from its ideal behavior, that is when gamma I is not equal to 1, is because of solute interaction. So we need a model for obtaining the energetics between a cation and other ions present in the solution. So there are different kinds of interaction. There can be electrostatic interaction, there can be hard sphere repulsion, and so on. Okay, so these have to be modeled. So how did Debye and Hückel view this problem? Intuitively, you would see that if you have a cation, on an average, surrounding a cation, there are more number of anions, and the other way around. That is, if you have an anion, on an average, there are more number of cations surrounding the anion. Also, what is seen is that these ions are not fixed in a lattice. They are mobile, and with these features, that is, that there are mobile ions, Debye-Hückel built a mean field theory. What is the mean field theory? So we spent a lot of time elaborating why Debye-Hückel theory is a mean field theory. So what they did was they focused on a particular ion of charge state, let's say Q. And then if all the rest of the ions in solution are not given any identity, they are smeared out in the surrounding medium. So if there is a charge state Q of this particular ion, if I integrate the charge of the rest of the system, just excluding this ion, I should have a charge of negative Q because the net solution is neutral. So I can define a field surrounding this central ion where certain field properties are well defined. The field properties can be the charge at a particular point, potential at a particular point, and potential gradient at a particular point. These are all field variables. So you've seen this kind of field description, especially in engineering, thermal temperature field. Okay, so all these things are field variables. You can define in a continuous manner as you vary the spatial position. But what is interesting here is we use the Debye-Hückel theory as a case study in the development of a mean field model. So it depends upon few other features. How do you use certain features of electrostatics to get the energetics? So electrostatics, as I said, it's a mechanical theory. There's no temperature in here, but we did introduce a temperature using Boltzmann distribution and then obtain a potential that is relevant to electrochemical systems. And then to solve the problem analytically, we use Taylor series. These are the central features that go into the formulation of Debye-Hückel mean field model. Because of spherical symmetry, the Poisson equation can be written in the following manner. This way of distributing ions is called the Boltzmann distribution. Here, the essential statistical thermodynamics of classical system is incorporated. So this is the potential felt by an ion Z with charge state Zi at a particular point in space where the potential is phi. So this quantity as an unit of energy that is compared here with the thermal energy available for the system. If a system is at temperature T, each degree of freedom has an energy equal to half kT. Okay, that's the equipartition theorem. Okay, so with the Boltzmann distribution, we have gotten temperature here and combine this with the electrostatics, Poisson equation, and Gauss law. We have a model for obtaining the energetics. So then we use Taylor's series and get the solution. The solution is obtained via an important quantity called the Debye length. Debye length gives you another, compares two quantities, the thermal energy divided by this quantity. This is the ionic strength present in the medium. If the concentration of the ions is larger, the Debye length is smaller. Okay, so what is Debye length a measure of? It is, supposing you take a charge Q, Debye length is a measure of how the steep the lack of charge neutrality falls. If Debye length is small, the system becomes charge neutral quickly, and if the Debye length is larger, it takes a longer distance for the system to be charge neutral. Okay, so I just keep moving from the central ion, and at some point it will be charge neutral and phi will be 0. Okay, so Debye length is a measure of such a length scale. So again, Debye length will be larger if T is larger, right? So when T is larger, these ions around the central ion will be smeared out to a larger length scale. So you should have a good feel for what Debye length means. So even though we are looking at electrostatics around a particular ion, similar principles are also valid for an electrode. With this, we could also compute the del phi using a Debye-Hückel theory. So let's understand this expression. This would have been the del phi for an ion in vacuum. Okay. So that will be 1 by R dependence. But because of the presence of other ions in a solution, there are two terms which are multiplied. There is an expression which is like an behavior of del phi for an ion in vacuum times there is an exponential quantity which varies exponentially, that is scaled where the distance is scaled by the Debye length. We also computed the expression for phi. So these are the central field quantities. Once these are well defined, we have everything that we need to know about the system. To connect it to the free energies, there is an additional work term which we didn't cover, which is covered in many textbooks of chemical thermodynamics. One particularly good presentation is available in the physical chemistry textbook of Castellan. Okay, so that's an excellent presentation of Debye-Hückel theory. So it involves certain other electrostatic concepts that needs to be incorporated. The self energy of charging a particular ion to the charge state Q, and some work interaction between the ion and all the other ions. Once both these things are incorporated, you can get the work done in assembling a system that is being presented connected to G. Once you have that, all the aspects of the problem are well defined. So we only looked at one aspect in the previous lecture. So, okay, we'll move on to the content of this lecture. We are getting more and more into the central aspects that makes electrochemistry special. Okay, so what we see here is what is called the Ellingham diagram. Okay, so with this, I am trying to bring out why electrochemical approach is way more powerful than thermal approach to undertaking a reaction. So this always fascinates me, this way I introduce electrochemical systems to incoming students. What is being plotted here is delta G on the y-axis, and there's a temperature scale. Look at the temperature scale. We start from very small temperatures to all the way to 2400 degrees centigrade. And there are other quantities. This is all from Wikipedia. You can look at this. And then what we are plotting is, for example, let's take a system which is these are not systems that are of esoteric interest. Okay, these are systems that have practical relevance. For example, in a solar thermal approach, this zinc and oxygen, giving zinc oxide, is a very important system that is really used in solar thermal approaches to solar energy conversion. So as you would know that when zinc combines with oxygen and forms zinc oxide, that would be an exothermic reaction. So all these things are oxidation reaction. Therefore, this would be an exothermic reaction. However, the exothermicity decreases as the temperature increases. Why so? Because whenever we dissociate an oxide, almost in all cases, what you see is that the dissociated product of an oxide, oxygen is always in the gas phase, so entropy will favor the product phase. Okay, so if you have an oxide, it dissociates into, let's say, metal plus oxygen. Entropy will always favor the product side. Okay, so this, if this statement is not clear, we can discuss this in our discussion session, or you can go and look up a chemical thermodynamics textbook. Okay, so when I increase the temperature, if I consider this equilibrium, the increase in temperature will always favor these products. Okay, but of course it takes very high temperatures to break these molecules. Okay, because the exothermicity of oxidation is fairly large quantity. I mean, it's fairly negative. Okay, so let us look at this quantity. Okay, so I am oxidizing hydrogen with oxidation, means just reacting with oxygen to form H2O. So if I have to thermally dissociate H2O, I have to go to very high temperatures. So there is a flat line. Why is this flat line? Because the number of gas molecules in the product phase and the reactant phase is one and the same. Carbon is a solid, so entropically that doesn't matter. Entropically, there is one molecule here and one molecule here, so the entropy doesn't make, the temperature doesn't make a difference to the entropy, so this is a flat line. In this case, temperature only this line has a different slope compared to all the other lines. Let's understand why so. So you have carbon, oxygen, but 2 CO. Okay, there are more products in the gas phase compared to reactants in the gas phase reactants. Therefore, increase in temperature tends to push the equilibrium to this side. Okay, so that's all not the issue here, but the main take home is that you have to notice the temperatures that are required for splitting H2O to H2 and O2. Okay, these are extremely high. So let us look at the thermodynamics of an electrochemical system. This splitting, water splitting into H2 and O2 can be achieved just at room temperature, right? You might have even done this experiment in your high school. This is a 5 minutes experiment if you have a good battery and water and 2 copper leads, right? This is a very trivial experiment. That is the remarkable thing about electrochemical, doing reactions via electrochemical system. These things that require extremely high temperature can be done at room temperature and pressure. Okay, so if only we have electrons, electricity available at a lesser cost, almost all the reactions would be conducted electrochemically. That's the beauty of electrochemistry. Okay, so you have here, we have already shown, this is the Pourbaix diagram of water. So it contains all the electrochemical thermodynamic information. So below a particular potential, when you go cathodic, you can evolve hydrogen, and beyond a particular potential, you can evolve oxygen. So if you have a water electrolysis setup, okay, so you have 2 copper leads, let's say, that's available to you, and then just have a battery. You have a simple, so any kind of battery, but the potential should be more than, let's say, 2 volts. We can split water into hydrogen, oxygen. Okay, so that is the beauty. That is, things can be done at room temperature and pressure, because all my energetics is modulated by potentials that are present at the electrode. Okay, so I have something that is able to overcome the thermodynamics, right? That is, thermodynamics of H2O to H2 and O2 is very endothermic. Okay, I have something which is able to overcome that endothermic thermodynamics, relevant endothermic thermodynamics. What is that something? That is the energy of the electrons which can be modulated by varying the potentials at the electrode. Okay, so that's the beauty. Okay, so I mean, this is not that important. Okay, so but what is much more important, because you have certain constraints on how much you can vary this, but the importance of electrochemistry is or the power of electrochemistry is how you can modulate the energy of the electrons by varying the electrode potential. Okay, so that is the take-home message from this slide. That is why electrochemical approach is way more powerful compared to the thermal approach. Yeah, so in fact, most of the chemistry of the human body is done electrochemically, okay? Because the body temperature is at a particular, it is a very narrow window that biological systems operate. So if you want to do the complex biochemistry that is seen in biological systems, there is an exquisite arrangement of electrocatalytic sites which makes possible all the biochemistry that you see in the human body. Okay, so we move on. So I said that we can attain a huge window of energy of electrons in the electrode. That is possible because of the nature of the electrochemical interface. Okay, so what is that I'm referring to? So that is being illustrated via a schematic. What we have here is an electrode that is, let's say in this case, positively charged. That is, I have removed some electrons from the electrode. Therefore, I have made the electrode positively charged. And then in response to the positively charged electronic conductor, which is the electrode, there is a charge accumulation at the electrode-electrolyte interface. Because this is positively charged, the ions are counter ions. There are net counter ions at the electrolyte near the electrode. Okay, so this is the electrode-electrolyte interface. If there is net positive charge here, there is a net negative charge here. Put together, this is called the double layer. Okay, electrochemical double layer. Okay, so this is where the power, all the mysteries of electrochemistry is, okay, in terms of chemical reaction. There is also, this is called electrodics, and the other part is how ions get conducted in the electrolyte, that's called ionics. Okay, so these are all of electrochemistry can be discussed between electrodics and ionics. So there is, if you are considering only the electrolyte, there is greater accumulation of ions close to the electrode. As we go away from the electrode, the accumulation of these negative ions decreases, and beyond a particular point, there is, the system is charge neutral. Okay, so try to connect what we did in Debye-Hückel theory to this system. There, our central ion was not an central system, reference system was not an electrode, but a spherically shaped ion. Okay, as we went away from the ion beyond a distance lambda, Debye length, the system became charge neutral. Likewise, we have a length scale, which is again the Debye length, beyond which the system, that is the electrolyte, becomes charge neutral. So where there is lack of charge neutrality, that region is determined by Debye length. All right. Let us look at this more closely. So you have two electrodes. These are two different systems. There is an electrode where there is negative charge, and there is another electrode, a different electrode, which is positively charged. This system is similar to this system, but we've added certain more details into the description. Let's understand the additional details. So here we have anions and cations. Typically, the notion from inorganic chemistry, there is some basis for that, is that the cations are smaller. Therefore, the water molecules, solvated water molecules, will bind to the cation to a greater degree. Okay, this interaction, this is a dipole, ion-dipole interaction. This is stronger interaction. Anions are larger. Therefore, the dipoles, water dipoles, are bound to a lesser extent. Therefore, what you see is that it is possible to strip anions of the water molecules, and the anions can directly bind to the electrode surface. Okay, that's a notion. Okay, these are all, where imagine, these are all great achievements of human creativity. Okay, our people, scientists, imagined all these things before anything could be visualized. Okay, via experiments. So they had some intuitive notions, ideas, and they formulated these ideas in terms of mathematical equations. Helmholtz did all these things. Just with at a time when none of these measurements of the state of the ions could be made. Okay, so now with great improvements in imaging, we can make these measurements. What is the structure of the ions on the electrode surface? But in the time when Helmholtz imagined all these things, none of these measurements could be done. So all the models were made by imagining how the interface would be. So because it is possible to strip off water molecules from anions, they can directly bind. Okay, so as opposed to that, when you have a negatively charged electrode surface, it is not possible to strip off cations. So the cations still bind through the water molecule. Both these systems are possible. Okay, so this is called compact. Okay, this is these ions are stuck to the electrode surface. They're not that mobile because of certain reasons. So that's called a compact double layer, and there is a diffuse layer. Okay, instead of diffusion layer, this could have been better referred to diffuse layer. I mean, we can justify this usage also, but we can take up these questions in the discussion session. All right, so this H, okay, refers to Helmholtz. Okay, so Helmholtz was early pioneer in this description of double layer. These were all done in 1800s. Okay, so this length scale, wherein there is lack of charge neutrality, again is given by the Debye length scale. Okay. All right, so let's go further. Let's go to an additional term. We described the structure qualitatively, but what is of more relevance to the nature of electrochemical system is how the potential falls off at the electrode-electrolyte interface. So, as I said, in the bulk, the system becomes charge neutral. The potential is zero. This is phi S refers to potential observed in the solution. This is the phi M refers to the potential at the metal. So there is there is charge accumulation, in this case negative charge. There is potential because of the charge accumulation, and gradually as you move away from the electrode, the potential decreases and asymptotically it goes to zero, right? So there are lots of features in this schematic. All these things can be rationalized because there is a negative charge here. There are more positive charge, even though there are some negative charge also being present, okay? Because entropy is such that you will have some negative charges also present here, but overall there are more positive charges that are being present here at this interface. And then the additional thing to be noticed is the water dipole is aligned because of the negative charges here. We also mentioned that it's not possible to strip off water molecules from the cation at the relevant temperature, okay? So if you, therefore, this cation binds to the electrode via the water dipoles, okay? And then lots of systems here, maybe here, in fact, I took the two schematics from two different textbooks. The anion and cations have different sizes here, okay? But that's a detail, okay? We can discuss these things in the discussion session, okay? This is called the inner Helmholtz plane. This is called the outer Helmholtz plane, okay? These are all, why did they define all these things? Because they had to build up a model for capacitance of an electrochemical interface. This could be measured even in 1800s. That's a macroscopic measurement of capacitance. We will look at this in much more greater detail when we look at capacitors, supercapacitors, and so on. These are all important power devices. We will build a quantitative model for capacitance. Helmholtz built all these things in 1800s. So he had to define this inner Helmholtz plane, outer Helmholtz plane to obtain a quantitative expression for capacitance. But what is of importance is that there is a steep fall in potential. Why am I saying it's steep? Is because the potential falls within this distance scale lambda, right? Within this distance scale lambda, the potential falls. So what does that give us? Because if I know temperature, if I know the concentration, I can get lambda, okay? Concentration of the ions, I can get the length scale lambda. I know I can measure the potentials by a simple voltmeter measurement. Because I know lambda, I can get the magnitude of electric field. Look at the magnitude of electric field. This is amazing, right? This magnitude of electric field is 10 to the 8 volt per meter, okay? This is a very high electric field, okay? So that's the beauty of electrochemical interfaces. And I can get these electric fields at room temperatures, okay? Room temperatures and pressure. So this is not a esoteric system, okay? The capacitance which you see in most of the normal electrochemical interface is not very high. Okay, this is just 0.3 farad per meter squared. Okay, so this is not a supercapacitor or something. If I just have a simple metal, I can get the quantitative estimate for capacity, the capacity present at that electrochemical interface. That is about 0.3 farad per meter squared. All right, let's move on. So there are certain jargons that you would see in electrochemical systems, because these jargons were developed because people imagine how the electrochemical interface behaved. Okay, so in early 1900s, okay, Faraday and lots of German chemists and English chemists developed a lot of these things, and French people, because that's where the center of research in electricity and magnetism was. Most of the research, most of the law which you see in electrostatics, Gauss law, Ampere's law, okay, all these things developed in Europe. And from electrostatics research, the offshoot of electrostatic research is the research and documentation of electrochemical systems. Okay, so again, all these things were done in Europe. So there are two limiting behaviors for the electrodes. One is called totally depolarized electrode. This is like a model, a reference system. This kind of behavior is observed asymptotically in a reference electrode. So what is that? It's not possible to change the electrode potential because there is a lot of current in this system. Okay, it's impossible to change the potential. This is called an ideally depolarized system. The other limit is the totally polarized system. Okay, you can keep changing the potential of the electrode, but you do not see any current response. Okay, so here you do not see change in potential, but you see very high current. Here is the other limiting behavior. You see large change in potential, but you do not see any current response. But a typical system is somewhere here. Okay, so there is, for a change in the potential of the electrode, that's what is being plotted on the x-axis, you do see some current response. I'll define what this is. Even this is not what is observed in most of the electrodes, because there are some activation barriers involved in the relevant electrochemical reactions. So what you observe experimentally is, for example, if I change the potential of the electrode, there are two possibilities in an aqueous system. I can get oxygen evolution when I move the potential to the anodic region, make the potential more positive, or I can get hydrogen evolution when I make the electrode potential cathode. Okay, make the potential negative. Okay, but what I see is that there is a certain window where I can increase the potential, but I don't see any oxygen evolution. There's no current at all. Okay, likewise, I can go in the cathodic direction, but I don't see any current response. Okay, in this window, there is only polarization and no current evolution. Okay, this is like this behavior. Okay, in this region, the electrode is being totally polarized. Okay, and then only beyond a particular potential, there is current evolution. Okay, so with this, I can define another quantity called the over voltage. Okay, or the over potential. Okay, so how is the over potential defined? Supposing I can define the minimum equilibrium potential for oxygen evolution. Okay, I can define the over potential of the system as the potential where you are in minus the equilibrium potential required for oxygen evolution. In this case, let's say we are discussing the over potential for oxygen evolution, I can define, based on thermodynamics, the minimum thermodynamic potential that is required for oxygen evolution. And I can define the O potential for the electrode as the electrode potential minus that minimum potential. So for oxygen evolution, there is a minimum O potential that is required. Okay, it's often called onset potential, let's say. There is a minimum O potential that's required for oxygen evolution. Likewise, there is a minimum O potential for hydrogen evolution. Okay, that is defined by the electrocatalytic properties of the electrode. Okay, so these are a lot of words. We'll elaborate on these words in the subsequent lectures, what we mean by electrocatalytic properties. But for now, I'm just defining a quantity called O potential, which is defined as the potential minus O potential for a particular reaction is defined as the potential of the electrode minus a thermodynamic, a quantity obtained from thermodynamics. So there can be different kinds of O potential. In fact, all the electrochemical systems will be quantitatively described using O potentials. There are three kinds of O potentials. Let's understand them. So this is called an ohmic O potential. What is the current response? If I keep increasing that O potential, I get a linear increase in current. This is just like an ohmic conductor. V is equal to IR, right? V is this ohmic O potential as a unit of voltage, and I, okay, I get a linear increase because in current because of a linear increase in ohmic O potential, okay? And then I have another behavior where the current saturates, okay? So even though I am increasing a potential, I do not see any increase in current, okay? Such a O potential will be referred to as will be related to transport properties in the electrolyte. We'll look at that after a couple of lectures, okay? But in the subsequent lecture, the next couple of lectures, we'll be interested in kinetic O potential. What is the behavior seen here? I have an increase in current, an exponential increase in current when I increase the kinetic O potential. Okay, so I can see an exponential increase here. There's an exponential here, increase here. Okay, so this will be our focus of discussion in the next few lectures. Okay, so this has to do with electrocatalytic reactions or electrochemical reactions that occur at the electrode-electrolyte interface. Okay, so that will be the focus of the next couple of lectures. So the mathematical description of electrochemical systems is obtained by what is called the Butler-Warmer equation, which we would look at in the next lecture.